So this is the way the current universe looks like. There's matter that makes up us, stars and galaxies. But there's no antimatter. As you know, this is a good thing, right? If we actually meet antimatter counterpart, the minute you meet, then we annihilate with each other. And that would be really dangerous. And as far as we can see in our universe, there's no part of the universe where we see matter and antimatter annihilating with each other, spraying a huge amount of energy. So what that means is that as far as we can see, our entire universe is made only of matter and no antimatter. So that's how the current universe should be. We clearly won, but we don't know why. So the only way we can sort of understand how the universe came to this kind of situation is this. Back then at the Big Bang, there was huge amount of energy, and energy created matter and antimatter. But as we have learned, matter and antimatter are always created in pairs, 1 to 1. So if there were 1,000,000,001 matter particles, there should have been also be 1,000,000,001 antimatter particles, equal in numbers. But if they stayed equal, they all annihilate with each other, and the universe should have become totally empty. But that's not the universe looks like to us. At least we exist. So we need to have remaining matter. So the only way that could be possible is that there must be some mechanism to pick one out of 1,000,000,000 antimatter and convert that into matter somehow, so that we have now 1,000,002 matter particles and 1,000,000,000 antimatter particles, so the difference of about 2 in 1,000,000,000. And only after that, matter and antimatter start to annihilate with each other, and then this difference of 2 remain, and that's us. So we believe this is the way we survived the Big Bang. Matter remained to date because somehow a part of antimatter got turned into matter, and they got reshuffled. But we don't know how, and that's the problem. So this is really a life and death question, as you can see. So if the world of antimatter is the exact mirror of the world of matter, then the universe could not have chosen matter over antimatter. It should have created the equal amount, and we should be gone by now. So there must be some reason for matter to be chosen over antimatter, which means there must be some subtle difference between the behavior of matter and antimatter. World of antimatter should not be an exact mirror of the world of matter. So how can such a difference be explained? And in the jargon of particle physics, this is called CP violation, and it doesn't matter. And there was a theory proposed by Mr. Kobayashi and Masukawa back in 1973, which was supposed to explain this subtle difference in the behavior of matter and antimatter, and that was awarded a Nobel Prize in Physics fairly recently. So what is that? So again, looking back at the structure of matter, we know, so we have atoms, electrons around it, atomic nucleus in the middle, made up of neutrons and protons. And neutrons and protons are further divided into these tiny quarks, proposed by Gell-Mann. We talked about this briefly in the previous lectures. And so if you look at this list, then everything around us is made of atoms, and therefore they're made of electrons, down quarks, and up quarks. And 2 down quarks and up quark would make up a neutron. 1 down quark and 2 up quarks would make up a proton. So everything around us seems to be made up of these 3 kinds of elementary particles: electron, down quark, and up quark. This looks like a fairly simple world. But when people start looking for various experiments and then particles coming from outer space, people discover the weird particle called muon. And as far as you can tell, the muon looks exactly the same as electron, but it's just heavier. And the property is exactly the same as the electron. And that's kind of strange. Why does nature need to repeat itself? We were okay with electrons alone. Why did we need the second one called muon? It's like a big brother of electron. Indeed, when muon was discovered, a Nobel laureate, I.I. Ravi, even said, "Who ordered that?" So no, we actually still don't know the answer to this question. Why does nature repeat itself? Even though the muons may not sound familiar to you, it's all around us. So if you build a device with very high electrical voltage, sometimes you see this bright orange line crossing it. You see it happen here, here. So the muons are coming from the sky, or outer space rather, and falling on us all the time. So as we speak, muons actually go through our body like X-ray, about 1,000 of them every minute. So there are tons of muons around us coming from outer space. And muons are not useless either. So one of my heroes in physics, Luis Alvarez, another Nobel laureate in physics from Lawrenceburg National Laboratory, actually decided to use muons to look for hidden chambers and hidden treasures in the Egyptian pyramids. So idea is very simple. There was a legend that one pyramid in Gaza had actually a hidden chamber. So there may be even hidden treasure in it. But if this is true, then this part has less rock than the other part. And if the muons go through these rocks, here you have less rock, so you lose fewer of them. But here you have more rocks, you lose more of them. So you would see some difference in the amount of muons coming this way versus that way. So he placed this detector in the middle of this chamber here and measured the flux of muons coming from that direction and that direction and compared them. That was a brilliant idea. Unfortunately, as a result of this measurement, he could show that there was no hidden chamber. Well, that's life. But anyway, so this kind of technique was published in Science back in 1970, and this inspired much more recent use of muons for practical purpose. You can see through a volcano. You know, volcano is a big thing. The muons come from outer space. They penetrate the volcano all the time. So you actually measure the muons going through a volcano. You can actually locate where magma is. And if you can see the magma rising up, then you can predict the eruption is in order pretty soon. So this is the way you can image a volcano by using muons. And this might actually help us predicting when the next eruption would happen in a given earthquake. So much about muons. So now this Luis Alvarez is one of my heroes because he is so creative coming up with this many interesting ideas. And not only he used these muons to study the Egyptian pyramids, he also is the person who actually pointed out this possibility that dinosaurs went extinct by the asteroid impact. So he was indeed a very creative guy. So now going back to the list of elementary particles, muon had been discovered, as I told you, but that was followed up with many other discoveries. We now found the sibling of down quark is called strange because it did indeed look very strange. There is now a big brother of the up quark. But before that big brother had been discovered, Kobayashi and Maskawa predicted that, well, if you have electron and muon, there must be actually a third one for that type. If they were down quark and strange quark, there must be the third one of the same type. And even though up quark was by itself at that stage, there must be another one, and yet another one, and that was their bold prediction. So how did they actually come up with this prediction? Well, it turned out that their prediction had been experimentally verified. As I said, the big brother of up quark had been discovered a year after they proposed this theory. And then another one, a year later, and 3 years later. And these circles actually drawn as the mass of these particles. The bigger the circle, the heavier it is. And the next one, after bottom quark, of course, there should be the third one beyond this charm. And that took actually a long time because that one turned out to be extremely heavy. And that is the particle called top quark. So indeed, their prediction turned out to be true. But I haven't told you yet why they came up with this prediction. There are 3 species for each type. And that is really had to do with this difference between matter and antimatter. So if you have 3 objects, then you can connect the dots, 1, 2, 3, and that will form a triangle. So let's say this is the triangle for matter particles. The world of antimatter is sort of a reflection of it. So now you can see that the matter and antimatter indeed look different from each other. But if there are only 2 of those, then you can connect the dots of 2 objects. And if you reflect it, you don't see any difference between them. Because line reflected, it still looks the line. So the world of matter and antimatter look exactly the same. So you need at least 3 objects for a given species so that you can tell the difference between matter and antimatter, and hence the prediction of having so-called 3 generations of particles for each particle type. And so that's the way they made the prediction, and now that was subject to a bigger experimental test. They wanted to test this prediction, how matter and antimatter would behave different from each other by building yet another type of particle accelerators, in this case colliding electrons and positrons. And there was a head-to-head competition between the team of Stanford Berkeley and a laboratory called KEK in Japan. And these are super high-tech machines. You need to have a micron precision over 4-mile range of aligning very high-tech instruments and colliding beams of particles every 4 nanoseconds at speed of light. That's a super high-tech machine, I would say. And using this machine, for example, this is the Berkeley-Stanford machine built in Stanford. You see the leader from the Berkeley side, Pierre O'Donnell, who came up with the idea of this machine, and Jonathan Dauphin, who was the leader on the Stanford side, and he is now the president of a university actually in Okinawa, Japan. And these accelerators, one was built by Stanford group, the other one was built by Berkeley group. This is for electron, the positron. This is for electron, and the Berkeley ring is even colored by Berkeley school color, actually, yellow and blue. So using this machine, they tried to measure the difference between the behavior of matter and antimatter, and they found a tiny difference as predicted by the theory of Kobayashi and Masukawa. So that tells you that there was indeed a difference between them, and I'm not going to tell much about the details of this plot, but one kind of particle called B meson, let's say this is a particle, and its antimatter version, anti-B meson, and they watched how these particles decay as a function of time, and you see clear difference between particle in blue and antiparticle in red. So indeed, particle and antiparticle behave slightly different from each other as predicted by Kobayashi-Masukawa theory. So that's good. But there was a catch. So because everything was as predicted, and that actually poses a new problem. Because the problem is that when the particles and antiparticles difference had been understood by the theory of Kobayashi and Masukawa, now we can predict how much of the difference in matter and antimatter we can get in the universe. Can we explain this 1 part in billion difference between matter and antimatter? The answer turned out to be we can explain only like 10 to the minus 26th. We are 17 orders of magnitude short. So it's clear we are still missing out some big difference we need. There must be more differences needed to explain the preponderance of matter over antimatter in our universe. We also haven't seen how matter and antimatter can be reshuffled with each other. That is something we have to look for too. So now is the question. Now that we know how the matter and antimatter behave different from each other in the study of quarks, but that wasn't enough, clearly. So where else can we look for possible difference between matter and antimatter?